welcome back to the another lecture of the NPTEL course on mechanical and electrical systems of mining machines. So we come to the third lecture on simple mechanism, which will be covered in module 1, that is in fundamentals of mechanical systems in mining machines. In first two lectures, we discussed about the overview of different machineries and the mining systems that are being used in different mines. So the concepts that we would be covering in this lecture, we would start with introduction, then we'll go to the kinematic pair, then we'll learn about the classification of kinematic pair, then we'll know about kinematic chain, what makes a kinematic chain mechanism. We'll learn about that. Then we'll go to the number of degrees of freedom in plane mechanism. Well, we will be learning about different criterions. And then at the end, we will end with the inversion of the mechanisms. Now, when in last class, we discussed about the different classification of machineries, starting from surface machinery or underground machinery, high-vol mining machinery, and so on. However, one thing we wonder, the huge machines, they are not made in one part. However, there are multiple small elements or components that combine to form a huge machine, which gives us some kind of definite work. Again, the different parts of the machineries gives us different kinds of action that we require for different operations. So first of all, coming to the introduction of this lecture, so what is a machine? So let us first understand, a machine is a device which receives energy and transforms it into some useful work. Now, when a machine has to do some kind of useful work, then it has multiple elements that act together to give some kind of relative motion with respect to each other. So let us take an example of one of the simplest machine, that is the steam engine. As you can see here, this is the steam engine where there is a base and then there is a flywheel to which a crank is attached, and then this blue component that we are seeing is the connecting rod, and this blue component is connected to the piston which moves inside a cylinder. Now in this we can see that the cylinder is again fixed to the engine frame. So here we can see there are multiple elements which gives us some kind of work with relative motion to one another, where we have this engine frame, the crankshaft, which is the element number 2, element number 3 is the connecting rod, and then it is connected to the piston which moves inside the cylinder. Now here as we see, the cylinder is fixed to the engine frame, making it a part of the element 1. So the two characteristics of the different elements that we call it as a link that we need for any machine to convert in any energy that it receives into useful work is it should have relative motion to each other and it should be a resistant body. Now here we see that this engine frame doesn't have a relative motion, however it is a resistant body. However, if we see the crank or the connecting rod or the piston, they have certain relative motion to one another, and such kind of elements which has relative motion to one another or is a resistant body, we call it as a kinematic link, which has the capability to receive energy and transform into some useful work. Now when we talk about these links, they are again of different types. They can be rigid link, they can be flexible link, or they can be fluid link. When we see that there is an element which does not deform while transferring the energy or transmitting the energy, then we call it as a rigid link. However, when we have a link like the chain that we see herein, it is capable of transmitting energy. However, it deforms while transmitting the energy. So that is why we call it as a flexible link. We also have another kind of link which we call it as a fluid link, which we generally see is used within a piston cylinder arrangement. Either if it is a case of a hydraulic press, jacks, or in case of brakes. In heavy machineries, mostly we see that in all the machineries or in any vehicle, we see there are brakes. It's not only the heavy machineries, but any small machines, we have brakes which is applied to stop any moving element. So this kind of element where we have a fluid inside a cylinder which transmits the power through the piston to any moving element, we call it as a fluid link. Now we have understood about link, which is the smallest element of any machine. Now when two links are joined together, they form a kinematic pair. So here as an example, you can see there is an element A where we have a shaft, and then there is an element B where we have a bearing housing. So these two link together, that is the shaft and the bearing housing, makes a kinematic pair. Now when we talk about kinematic pair, let us try to understand what are the different types of motions, or to be specifically told as a constrained motion that it interacts with each other. Let's say we have a square hole and we have a square bar. So and they are amalgamated together, or you push this square bar into a square hole, you can see there is only motion in one direction. Not, it cannot rotate or it cannot move in the second and third direction. So this kind of motion, we call it as a completely constrained motion, that we need it to move in one direction and it is moving in only one direction or the definite direction. However, when we have a round shaft and we have a round hole, and when they are mated together, so here we see that the shaft can move forward and backward. However, it can also rotate inside this round hole. So such kind of kinematic pair, we call it as the incompletely constrained motion. Now when we call a kinematic pair to be have successfully constrained motion, when we have, let's say an example, we have a footstep bearing and we have a shaft, and an external load is applied to keep these two elements in place, we call it as a successfully constrained motion. Now, how do we classify the kinematic pairs? So we can classify it in three categories. So the first category is according to the type of relative motion between the elements. So there are 5 different kinds under this category, where the first one is a sliding pair. So let's say we have a shaft and we have a hole, and we have to like this shaft goes inside this hole where there is only surface contact, we call it as a sliding pair. Even the best example of a sliding pair is a piston and cylinder arrangement. Now when do we call it as a turning pair? So let's say we again have a shaft which goes inside a hole and the shaft rotates inside the hole. So that we call it as a turning pair. So one of the most common example that we see is the lathe spindle supported in the headstock. So the third type is a rolling pair. So all of us know how a ball bearing looks like. It can be a ball bearing or it can also be a roller bearing, where we have a bearing house, and inside that, in the inner house, we have multiple balls which helps in transmission of motion. So this ball rolls inside this inner housing of the bearing, which we call it as a rolling pair. Now when we come to screw pair, the best example is a nut and bolt, which many of us have seen. So there are threads where we see in one of the element there is thread and there is a nut which moves over this thread. We call it as a screw pair. So the last pair in this category is the spherical pair, in which we have a socket and inside that we have a ball which moves inside the socket. So we call it as a spherical pair. So the example of it is the attachment of a car mirror, or you can see your arm, where your shoulder is there is a socket in your shoulder and your arm can move inside the socket, which gives you a perfect example of spherical pair. Now, according to the type of contact between the elements, your kinematic pair is classified in two categories. One is the lower pair and the other is the higher pair. In lower pair, when there are two elements which have surface contact with each other, let's say there are two elements which have surface contact with each other, then we call it as a lower pair. However, when we have a point or a line contact, we call it as a higher pair. So one of the examples you can see in this gears. So more about it, how it is a point or a line contact, we will be learning when we go through the toothed gears. Now, the third kind of classification is according to the type of closures. So there are some self-closed pairs and there are some forced closed pairs. So the example of the self-closed pair you can see herein, where there are multiple elements and then we close the different elements with different types of or different nut and bolts here, or we can say different elements, they are assembled together without any external effort. We call it as a self-closed pairs. However, when there is an external force that has to be applied for two link to be in contact with each other, we call it as a forced closed pair. As you can see here, there is a spring which forces the two elements to be in contact with each other. So one of the perfect example is cam and follower, which we will be learning in details while we go through the internal combustion engine topic. Now we have learnt about links, then we have learnt about the kinematic pair, then we will learn about the third term, that is the kinematic chain. So what do we understand as a kinematic chain? So we have number of pairs. So here we see that there are four links, that is 1, 2, 3 and 4. So when the first link, that is the link number 1, goes around to the last link and the last link is connected to the first link, we call it as a kinematic chain. So which is able to give or transmit a definite motion. So if it is not closed, we cannot call it as a kinematic chain. So as we can see the example herein, the engine frame is our first link, our crank is the second link, connecting rod is the third link and the piston is the fourth link. The cylinder is attached to the engine frame, which becomes a part of the first link. So here our first link and last link are connected in a way so that there is a definite motion that can be transmitted. What is the definite motion here? It is the rotation of the crank gives us a reciprocating motion of the piston inside the piston cylinder arrangement. However, there are certain rules that applies when there is a kinematic chain. So the first rule it's a thumb rule which relates the links, the number of links with the number of kinematic pair. So as we see herein, the number of links here is 4 and the number of pair is AB, BC is one pair, BC and CD is another pair, CD and DA is another pair. So the last pair is DA and AB. So we have 4 pairs. So our LHS is L, our RHS is 2 multiplied by 4 minus 4, which is again 4. So our LHS here is equal to RHS, which satisfies the equation of this kinematic chain, which we call it as a 4-bar chain mechanism. Now we will talk about what is mechanism in the subsequent slides. However, let us come to the second thumb rule, where we have this expression which needs to be satisfied, where J is the number of joints. What do we consider as the number of joints? Here we can see A, B, C and D. They are the number of joints. And when we talk about number of joints here, to be specific, they are number of binary joints, which we call it as here 4. So here A, B, C, D, there are 4 joints. So J is 4. Now what is the number of link? It is also 4, 1, 2, 3, 4. So J is LHS, L is RH, L is we have to put it in RHS. So which is 3 by 2 multiplied by 4 minus 2, which is 4. So again we see here these two equations are satisfied in this kinematic chain. So when there is any kinematic chain, so these two kinds of these two equations have to be satisfied. Now there is another disclaimer here. These equations are applicable only to kinematic chains in which lower pairs are used. That is, there is surface contact. So these equations can also be applied to kinematic chains which utilizes higher pair. In that case, each higher pair may be taken as equivalent to 2 lower pairs. So let's say if there is a point contact or a line contact, we would consider it as 2 lower pairs because point and line contact are higher pairs. Now going in details of the types of joints in a chain, that is a kinematic chain, we understand what is a binary joint. When there are 2 elements or 2 links joined at one point, we call it as a binary joint. So here we have A, B, C and D as a binary joint. So one of the example of the binary joint you can see herein. Now coming to the ternary joint, here you can see there are multiple links which are joined together to form a kinematic chain. So you can see there are 6 links which are there. However, at joint number E and C, we see that there are 3 links which are joined together at a single point to give you a ternary joint. So there are 3 links, 6, 5 and 4, which gives you E, and 2, 5 and 3, which gives you C. Now coming to the quaternary joint. So similar to ternary joint, when there are 4 links which are joined together at a single point, we call it as a ternary joint. So here in this figure, we can see there are 11 links. However, at the point G, we can see there are 4 links, that is 11, 10, 8 and 7. They are joined at one single point to give you a quaternary joint. Now, what do we understand is, in case of a quaternary joint, it is equivalent to 3 binary joints. So, what is the rule? When there is L number of links which are joined at the same connection, so the joint is equivalent to L minus 1 binary joint. So, here there are 4 links. So, the number of binary joints that we have here is 3. L is 4. Our binary joint becomes 3 here. So, many of you would be having question that how is it 3? It can be 4. So, we go here clockwise, and what do we see? 11 and 10 make one binary joint, 10 and 8 make another binary joint, 8 and 7 make another binary joint. We do not count here the last pair to be a binary joint. Now, after the kinematic chain, we need to understand another term that comes thereafter is the mechanism. So, now we have link which are joined together to form the kinematic pair, and now there are multiple kinematic pairs where the last link is joined to the first link to form a kinematic chain. However, when do we tell a kinematic chain to be a mechanism? When it is able to transmit a definite energy or transmit definite motion. And there is also another catch or a difference between the kinematic chain and mechanism is, in a mechanism, one of the link is fixed so that the definite motion can be transmitted from one link to the other. So, as you can see in the example herein, here we have this black link which is fixed. Now, the red link is rotating, the green link is transmitting, and the blue link is following, which we call it as a follower. So, we can see here a rotary motion is very well converted into a reciprocating motion when one link is fixed and one link acts as a connecting link. Now, when we talk about mechanism, so when there are 4 links, we call it as a simple mechanism. However, when there are more number of links, then we call it as a compound mechanism. So, when we talk about more number of links, it is more than 4 links, we call it as a compound mechanism. So, the example of a simple and a compound mechanism is shown in the figure herein. Now, we may have a mechanism, but in order to have a definite power transmission or definite work output, so the links in any mechanisms have to be arranged in a certain way that they give certain amount of power or useful work. So, then we call a mechanism as a machine. Here we will talk about the 4-bar mechanism, where we have 4 links and 4 joints. Now, in this 4-bar chain mechanism, we don't know as of now what would be the degrees of freedom. Now, let us separate all the links out of this mechanism and take the links separately in XY coordinate system. So here we see that we have kept the AB link, that is a fixed one, on the X axis. However, we have taken the link CD, that is the link 3, in the XY coordinate space. So here this CD can have 3 degrees of freedom. How? It can move in X direction, CD, it can also move in Y direction, and also it can rotate about this axis. So where we have theta. So here the degrees of freedom of CD is 3. Now when we join the point D with A, so its degrees of freedom no longer remains 3. It comes down to 1. So how is it? Because your CD cannot move in X direction, it cannot move in Y direction. However, it can only rotate about this axis with theta. So it has the degrees of freedom n is equal to 1. So when we take all these 4 links in the XY coordinate space, here we see that the link 1 is fixed. So it does not have any degrees of freedom. Now when we talk about the link 2, it has degrees of freedom as 3 because it can move in X, Y, and it can also rotate. For link 3 also the degrees of freedom is 3, and for link 4 also the degrees of freedom is 3. So the total degrees of freedom in this system is 9. Now when we join the link 4 to link 1, now here the degrees of freedom of link 2 is 3, for here 3 is 3, and for 4 it becomes 1 because it cannot move now, it cannot translate in X and Y direction, it can only rotate in along with this respect to this link 1. Similar way, we now fix our link 2 with 1, where our degrees of freedom of link 2 becomes 1, and link 4 we already know it is 1, but for link 3 it is still free in the coordinate space. So here our n is 3. So this gives us the degrees of freedom for this system as 5. However, when we join the link 3 to link 4, our degrees of freedom for individual link becomes 1. So summing it up, our total degrees of freedom for this system is 3. Now when we join the last link with the adjacent one, here we see that there cannot be any kind of motion. There can only be one kind of motion, that is theta, and the others follows to this motion that is given to one link. Hence our degree of freedom finally boils down to 1. Now how do we know? Like for a very simple mechanism, that is a 4-bar chain mechanism, we could understand that we could do it in this format. However, when there is a complex mechanism, how would we go ahead with it? So we have a equation for the number of degrees of freedom for a mechanism, which is given by n is equal to 3l minus 1 minus 2j minus h. So here n is the degrees of freedom, l is the number of links, j is the number of binary joints, and h is the number of higher pairs. So this equation we call it as the Kuchbek criterion for the mobility of the mechanism having plane motion. Now when we have the higher pair is 0, so our equation boils down to n is equal to 3l minus 1 minus 2j. Now let us try to solve some of the example problems here where we have different types of mechanisms. So here for a 3-bar mechanism, what would be our n? So here our, what is L? L is 3. What is the number of joints? Joints are also 3. So our equation of n is equal to 3l minus 1, that is 3 minus 1 minus 2 into 3, and we do not have any higher pair. So here our n becomes 0. So for a 3-bar mechanism, our degrees of freedom is 0. Now for 4-bar mechanism, we have already done it in the previous slide. Let us come to the 5-bar mechanism. So here our L is 5, J is also 5. So our n is 3, 5 minus 1 minus 2 into 5, which is equal to 2. So our degrees of freedom for a 5-bar mechanism in such a setup is 2. However, in this kind of 5-bar mechanism where we have a diagonal link, how do we find? Our L is 5, our joint. Here the joint is the binary joint. So now here this is a ternary joint, A is a ternary joint, C is also a ternary joint, which is equivalent to 2 binary joints. So here it is 2, 2, and here D is 1 and B is 1. So number of joints we have is 6. So here again solving the equation, we have minus 2 into 6, which is equal to 0. So for this kind of 5-bar mechanism, our degrees of freedom is 0. Now for a 6-bar mechanism, here our number of links is 6. However, when we talk about joints, we have 1, 2, 3, 4, and they all are ternary joints. So the number of joints becomes 8. Number of binary joint becomes 8. So here we solve it, 3, 6 minus 1 minus 2 into 8, which is equal to minus 1. So now can we have a system where we have the degrees of freedom as minus 1? So what we understand here is when there is when your degrees of freedom is 0, this is the mechanism cannot have a definite motion. So we call it as a structure. However, when there is the degrees of freedom is 1, that is for a 4-bar mechanism, so we can give only single input motion. When the degrees of freedom is 2, then there can be 2 separate input motions which are necessary to produce constrained motions for the mechanism. However, the last case where our n is equal to minus 1, this kind of system we call that it as the statically indeterminate structure, because there are additional constraints which are given to such mechanism which is not necessary. So that is why we call it as a statically indeterminate structure. Well, when we talk about the Kuchbach criterion with higher pairs, so let's say here we have a mechanism something like this, which you will be very well seeing if you see it for the power supports that are being used in the underground machineries in longwall mining. So there you would be seeing there is a lemniscate uh, linkage, so which is based on a 3-bar mechanism. So it completely follows this kind of um, mechanism that you see here, where 1 is fixed, 2 is one link, and 3 would follow, where we have some kind of, it's an advanced system, so you can see there are piston cylinder arrangements which helps you in the movability of your link number 2. So here in this case, how do we find the degrees of freedom? So again, we see here our link is 3, your joint, binary joint is 2. So here you see we have binary joint here 1 and here is 1, which is 2, and we have one higher pair which is between 2 and 3. So here it is a line contact that we see between number 2 and 3. So our equation for degrees of freedom comes down to something like this, which gives you the degrees of freedom of 1. So it is not always that when there is a 3-bar mechanism, it is a structure. But in certain case where there are higher pairs, there can be degrees of freedom, as you can see in case of power supports in underground machineries. However, when we talk about a 4-bar mechanism, here you can see that the number of links are 4 and the number of joints are 3. How 3? Here we have one joint, another joint, and this is the third joint where your link 3 is joined to link 4. Here your link 4 and link 1 does not have a binary joint. It is a higher pair. So there you get a degrees of freedom 2. So 1 is when the 2 would rotate, the wheel would be moving back and forth, and there will be also movement between the link number 3 and number 4. So when this kind of system, in this kind of system, the degrees of freedom becomes 1. When the friction between the wheel and the surface is high enough, then the degrees of freedom will boils down to 1. Now coming to the next criterion, that is the Grubler criterion, which also is defined for the degrees of freedom of a system. However, in Grubler criterion, we tell that the mechanism has the mobility of a mechanism is unity. So here in the place of n, we put it 1, and our equation, after putting it in Kuchbach equation, it comes down to something like this. So the simplest possible mechanism of this type are the 4-bar mechanism and a single slider mechanism, in which your number of degrees of freedom or the mobility is 1. Now there is another term which we call it as the inversion of a mechanism. So what is the inversion of a mechanism? We have understood about a 4-bar mechanism where we have fixed the link 1 and then we have given certain kind of motion to the link 4 so that the link 2 would follow it. However, we can do in other ways where we can fix the 2 and we can make link 1 free and try to see some definite motion. So in such way we can have 4 different inversions of a 4-bar chain mechanism, which we call as the inversion of any kind of mechanism. This is the example that I gave for a 4-bar chain mechanism. However, the inversion of mechanism for any other kind of more number of links is also possible. Now, when we talk about the different types of kinematic chains or the inversion of 4-bar chain mechanism, there are 3 different types. That is a 4-bar chain or quadratic chain, cyclic chain, as you can see here, as we have been discussing till now. Then we have the single slider chain mechanism, and the third is the double slider chain mechanism. So you can see here there are 4 links that are being used for transmitting definite power. When we talk about 4-bar chain mechanism, we understand that there are 4 turning pairs, that is A, B, C and D, and then there are 4 links, which is 1, 2, 3 and 4, and those are of different lengths. So there is a law which relates the length of any mechanism. What does it tells? The law is given by Grashof, which is known as the Grashof law of a 4-bar mechanism. It tells that the sum of the shortest and longest lengths should not be greater than the sum of the remaining 2 link lengths. So here the shortest is 4 and the longest is 2. So if we sum the length of 2 and 4, it will not be greater than the sum of the length of 1 and 3. So here what do we understand? That the shortest link will make a complete revolution relative to other 3 links if it satisfies the Grashof law, and that we call it as the crank or the driver. The link 2 makes a partial rotation or oscillates, and it is known as lever or rocker or follower. So here we have the link 2, which we call it as a follower. Your link 3 is the connecting rod and link 1 is fixed, which is the frame of the mechanism. Now coming to the last topic of today's lecture, that is the inversion of a 4-bar mechanism. In this slide, I have shown 2 examples of the inversion of a 4-bar chain mechanism, where we have 4 links, link 1, 2, link 3 and link 4, which gives us, which is not a steam engine, but it is a beam engine, where you can see the crank is rotating and it is transmitting the power to link 3, which is joined to a lever, and on the other end of the lever it is connected to a piston which moves inside the cylinder to do certain kind of useful work. The second kind of example of a 4-bar chain is the coupling rod of a locomotive, which we also call it as a double crank mechanism. Here we see that there is one link which is fixed between 2 wheels, and then there are 2 links, that is link 2 and link 4, which are connected to the wheels, which is again connected, these 2 points are connected by link 3. So since the length of link 1 and link 3 are same and link 2 and link 4 are same, so as the link 2 rotates, the link 4 would rotate. So this, we generally find this kind of mechanism in locomotives. So with this I end today's lecture. So the reference for this lecture, you can follow Khurmi and Gupta book, Theory of Machines. And if you have any doubt, we will be clarifying it in the online sessions. Thank you so much.